We've now seen and heard a lot about the flow of current in a circuit. But in everything we've seen, the current has always been flowing around in one direction. Such a current is called direct current, DC. In real life, the direct current causes a steady reading to one side of zero on the measuring instrument. But current also exists in a different form, in which the direction of the current goes first one way and then the other, and of course is called alternating current, AC. Here an alternating current is causing the pointer in the instrument to swing first to one side and then to the other side. But this is a very slow alteration, and the sort of AC we will be dealing with changes direction many times in a second. Power generation and transmission for our homes is AC, and there are excellent reasons for preferring AC to DC. Cities, towns, and villages all over the country need enormous amounts of electrical power. To make this power available cheaply, it is distributed at very high voltages, which are far higher than we can safely make use of in our homes. In other words, before we can safely use the power, we have to reduce the voltage somehow. Now it so happens that electrical devices known as transformers can easily change the voltages of AC, either up or down. Transformers cannot change DC voltages. There are literally hundreds of bits of electrical equipment requiring a lot of different voltages. And again, if we use AC, we can make use of transformers to produce exactly the right voltage for each piece of equipment. Alternating current, like direct current, is measured in amps, but with a difference. Let's see what the difference is. Take 1 amp DC. When 1 amp flows, a known, very large number of electrons passes a point in 1 second. Well, it's the same for AC, except that the electrons flow past the point in one direction, then reverse and flow past in the other direction. Suppose we have a simple circuit in which, using some sort of switch, we can make the current flow either way through the resistor, and we plot on a graph the current flowing at any moment. For a little while, with the switch open, there is no current flowing. Then we switch the current on in the positive direction, and at once we have a positive current flowing in the circuit. We show it above the zero line. Then we quickly reverse the direction of the current, so that we now have a similar negative current flowing, and we show that below the line. Every time the current reverses, the graph moves to the other side of the line. This is a waveform of a simple alternating current. Now in most circuits, in practice, it isn't a sudden instantaneous switch of direction like this. Usually the current builds up one way and then decays down through zero to build up again in the opposite direction, before decaying back again to zero. Gradual build up one way, decay. Build up the other way, decay again, and so on. This produces the sine wave. As well as showing the current flowing, the sine wave also shows how the voltage is varying. Starting at zero and going through the complete series of changes, through zero and back to zero again, we say that a cycle has been completed. The time taken for a cycle is called the period. If in 1 second 4 cycles have been completed, we say the AC has a frequency of 4 cycles per second. In this case, the period, the time taken for 1 cycle, is of course a quarter of a second. And from this we can see a relationship between period and frequency. Period equals 1 over frequency. The 50-cycle AC of the British National Grid has a period of 1/50th of a second. Incidentally, instead of saying cycles per second, we use the name hertz. In the United States, all electricity is generated at 60 hertz. The AC supply in a ship is usually 60 hertz, 60 cycles per second also. So diagrams like this are often used to illustrate alternating currents and voltages. And as we heard, this particular one is called a sine wave. The peak value of the current, one way or the other, is called the amplitude of the wave. Sine waves representing AC can differ in amplitude depending on the peak values of the current. And also they can differ in frequency from short peaky waves to broad shallow ones. And they can differ in another important respect which we need to know about. Here are two waveforms of the same frequency, but with different amplitudes. However, they do pass through zero and come to their peak values at the same time. We say that they are in phase. Now, suppose that one waveform is shifted to the right, so that the zero values and peak values no longer occur at the same time. The two AC waveforms are said to be out of phase, and the difference between them is called the phase difference. There's one final thing we must know about AC. Suppose the peak value of this AC is 1 amp. It is only 1 amp at 2 instants during the cycle. So it will not provide as much power as a direct current of 1 amp, which is at 1 amp all the time. Although the peak value of the AC is 1 amp, its effective value is considerably less than 1 amp. In fact, there's a formula for the effective value of the alternating currents or voltages. Its effective value equals 0.707 times peak value. For example, an AC of peak value 10 amps has an effective value of only just over 7 amps. The effective value of an AC is called the root mean square value, or RMS value. So the RMS value equals 0.707 times peak value. When alternating currents of voltage are specified, it's always the RMS value. For example, the household voltage of 240 volts is the RMS value. The peak voltage is in fact nearly 340 volts. And now let's sum up. We know what an alternating current is, and that it is most useful where large amounts of power have to be transmitted, and where voltage changes by transformer are required. We have learned what we mean by period and frequency and the relationship between them. We've become familiar with the sine wave way of showing alternating currents and voltages. And finally, we heard about RMS values. In the next part, we'll be thinking about the important topic of induction, which will lead us straight to the transformer and how it works.
Baby, take my hand, follow me. Let's leave this world behind, set us free. And I will give you everything that you need.